to attend the presentation of Professor Strong. Those who were here in the first presentation, I already presented him, but I saw new faces here. So we have to introduce him again once more. So,
this is a musical introduction.
Okay, so Professor Strong is a friend of mine. We met 30 years ago when I was a student in China. And Professor Strong at that time has already a PhD in mathematics and came to China to teach. That's where we met for the first time. So after he left China, he went back to the United States and got another PhD in physics. So he has 2 PhDs now. And of course he can speak English and fluently Chinese and also French. Okay, so Professor Strong worked for Motorola, and this some work in digital wireless baseband signal processing, network security, and also chip performance. And he also very much interested. Before that, after that, you work at the university?
Yes, that's right, after that.
So he's now a professor at Texas A&M in the United States. He's very much interested in applying his knowledge in mathematics and also interested in helping Africa. So if he has a small time, he always travels to Africa to help. So he has traveled to many countries in Africa: Benin, Chad, Cameroon, Nigeria, Sudan, where he gives lecture to students, and also he's very much into helping and spread the good news in terms of the research. So he has actually developed some tutorial in mathematics that could be helpful for us. He has 9 patents in the United States, and presently is still working on publishing some books.
Yes.
That is okay. So the presentation, the first presentation made was on agent-based things, and that is much more have to do with computational intelligence, and this one is more on optimization. And so please join me to welcome Professor Strong.
So first I wanted to say that if you went to my last talk, I didn't wear like this. I wore this to make Professor Foley more comfortable. In fact, this was given to me by a mutual friend. So I'm wearing this in honor of Tagaji. Okay, so today I'm going to talk about a technique. So like my last talk, I want to kind of focus on the top level. So you may not be interested in my particular application, but I hope that you can look at the methodology and think that it may apply to some problems that you are working in or interested in. So I have my name, and I have 2 students that I worked with on this. Tad Labor, I'm still working on this. Lucas Branch, well, I'll talk a little bit more about that. He was a military student and kind of got me started on this. So here's the outline of my talk. First, I'm going to give a short advertisement for the book that Professor Foley mentioned, and then just some very overview of what dynamic programming is, and then I'll go into some particular examples. I think that the way to really understand any kind of methodology is see how it's applied to an example. So the Gauss-Viterbi is very easy to understand, I think. So I chose something very, very simple, and then the complication ramps up from there. Okay, so short advertisement. The book that I'm editing is called Implementations and Applications of Machine Learning, and if anybody is doing something related to machine learning and has an application I'm very interested in soliciting chapters. The deadlines are already completely inaccurate, so there's plenty of time if you're involved in machine learning. So machine learning basically is a very broad topic and involves basically some kind of computers doing things in an intelligent way. Okay? So here's some contributions. We have many different types of applications. This one is power systems. This one is yeast, vanilla production with yeast. This one also is yeast. So I think we have some other involved with power systems. And there are many different techniques within machine learning that we're interested in. So the idea is to focus on applications that people can understand and get some idea of the possibilities of machine learning. So I'm co-editing this with Professor Subair from Sudan. Okay, so let me get into dynamic programming in particular. Dynamic programming is a technique that can greatly reduce the number of computations required to calculate an optimized outcome out of a very large set of possible outcomes. So you have a very large, what you call state space or search space, and you're trying to look within this entire space for the best solution. And the space is too big to search through. So you want some way of focusing in on where the best solution will be. So what you do is you take a large problem and you divide it into smaller sub-problems that you solve one by one. And these sub-problems in turn divide into individual cases that also can be examined one by one. So in some way you can think of dynamic programming as divide and conquer. Okay? And the key to dynamic programming is use the information that you've gained from your previous search to steer the search in a good direction. Now, one of the, here's my high-tech slide to illustrate. One of the examples that people use is looking for, you have some game reserve and you're looking for a lion. Okay, so you have some way of detecting, that detects say infrared or something like that, some way of detecting location of animals. So you have this big square game reserve here and you're looking for the lion. And the idea is that the larger area you search, now what you could do is just try to search one by one, scan through the entire region, and that's going to take a very long time. Okay, so what you want to do is something that's more efficient. So you have some way of looking at this area, and the larger area you look at, the worse the resolution. So if you're looking at the entire area, you can only tell up to which quadrant where the lion is. So you have some infrared signal and you can tell, well, okay, my signal tells me that the lion is in this quadrant. Okay, then you focus your attention on this quadrant. Okay, since you're looking at a smaller area, you have a finer resolution. So if I look at this quadrant, I can divide into 4 regions and I say, okay, now I can detect that the lion is in this quadrant. Okay, then you focus in on this quadrant. You have smaller region, finer resolution. You say, okay, the lion is in this quadrant. And you go down like this, down farther and farther. Now imagine if you took this entire square and you divided it into small squares of this size, and you wanted to search through all of these squares. That would be a lot of squares to search. But you see now I've already gotten down to this resolution with only 4 searches. So I've saved myself a large amount of computation because I've used my past information to steer my search in a direction where the line has to be. Okay, so this is really the whole idea, and every application is just more complicated applications of this idea. So if that's all you want to get, you can go. So that's all I'm going to talk about. Okay, so now how does that work in practice? So here's one example. Looking at DNA sequences. So I'm sure you've heard of DNA. It's the chemical basis of life. It gives genetic information. DNA molecules consist of nucleotides. Nucleotides, there are 4 types of nucleotides. And DNA has 2 strands that form a helix, and each strand has a sequence of nucleotides, something like this. Okay, so you have some sequence of nucleotides, and you may know the other strand will have the matching nucleotide. So I think C and G match together, A and T match together. So you have a string of nucleotides. So you can think of this as basically it's a message, like a message. Now, the type of information that's encoded is reflected in the frequencies of the nucleotide. And I'm not a biologist, but I got this from some other reference, and apparently you can have some type of information that has high GC content and some type of information that has low GC content. So in one particular strand of DNA, you may have some region of high GC content and another region of low GC content. And they may alternate. They may go high GC, low GC, high GC, low GC, something like that. Okay? So the question is, how can you look on the molecule and look at the sequence and determine which regions are high GC and which regions are low GC? Now, of course, it's not obvious. The DNA molecule is not saying this is high GC and this is low GC. You have to look at the statistical properties of the frequencies of these DNA nucleotides and try to estimate, get your best estimate of where is high GC and where is low GC. Okay? So that's the basic idea. You're looking at this sequence, and you're trying to classify parts of the sequence as high GC or low GC. So it's a classification problem based on this data. Some people may know something about hidden Markov model. This is an example of a hidden Markov model. If you're not familiar with that terminology, don't worry about it. So here is what we would call a Markov representation. If I start at the beginning of the sequence, I don't know if it's starting out in high or low. So at the beginning, I say, from when I start my search, say it's 50-50 probability of being high or low, right? Now, I look at the nucleotides one by one. If the DNA sequence is in high GC state, these are the relative frequencies of the different nucleotides. Okay? So you can see C and G have 0.3, 0.3. So they have 30%, but each have 30% chance of being C or G. Here, this is low GC state. In this case, G and C have only 20% possibility at each step. Okay. Now we also have these. I'm sure that they've observed data and things like this. This is the data that they gave me. That if one particular nucleotide, if one section is in high state, the probability that it will change will remain in high state is 0.5. The probability that it will switch to low state is 0.5. So if I'm in high state now, then the probability the next nucleotide is also in high state is 0.5. Probability the next nucleotide is in low state is 0.5. You see that 0.5 plus 0.5 add up to 1, because the next one will be either in high or low, so you need to have one total probability. Now, if the nucleotide is currently, if the DNA sequence is currently in low state, the probability it remains in low state is 0.6. The probability it moves to high state is 0.4. Whoops, sorry. I didn't mean to do that. Okay. All right, so again, if you're familiar with Markov chains, you can represent this system as a matrix. But here's a schematic representation. You're going to be moving from high to low state. You don't see whether you're high and low state. You only see the AGCT. And you want to infer from the AGCT whether you're in high state or low state. You're trying to infer that. And you will not get an exact answer, but you can get a best answer. So the idea is to find the most, did I say that? The idea is to find the most probable sequence. You're not going to get it exactly, but you want to at least try to identify the most probable sequence. Okay. So let's go on here. So here's what we can do. I want to represent this as what I would call trellis. Now, this is very interesting for me when I start getting into this, because the name Viterbl is very familiar to me from digital communication. And if you know about anything about the history of digital cellular, Viterbl was the one who kicked it off. And in fact, the entire reason why we moved from analog to digital was Viterbl employed this method to decode digital wireless. So what I'm talking about here is a simple version of what Viterbl did, and it's basically the basis of your 3G, 4G cellular systems, is a decoding system that's based on this method. So here I'm doing a simple case where my observed sequence is GGCA. Okay, so just an example. Okay, so at the beginning, again, when I start, I'm starting at the beginning of the sequence. I don't know if it's high or low. But I do have this information. I know that the first one is G. I know that the first one is G. Now, from my table here, I know that G has probability 0.3 in high and 0.2 in low. Okay? So the probability of a sequence where the first one is G and it's in G high state is 0.5 because I have 50-50 times 0.3 because 0.3 is the frequency of G in the high state. So I can assign a probability of 0.15 to G in the high state. Okay, now in the low state, the frequency of G was 0.2. That's what I have down here. Frequency of G is 0.2. So when I'm starting out, I have, again, 50-50 probability, that's where the 0.5 comes. Then the 0.2 comes from the fact that G in the low state has probability 0.2. Right? So I can assign probabilities of G high, 0.15, G low, 0.10. Okay, so that's not telling me that I'm in the high state yet, but it does give me some relative probability. Okay, so that's my first stage. Let me go on to the second stage. Now notice what I'm doing here. I'm breaking the whole entire sequence up into a sequence of subproblems. It's like I said in dynamic programming. I'm going to solve this one by one and then cut down the probability. Now, if you think about it, if you think about the number of possibilities for high and low, there's 1, 2, 3, 4 stages here, 4 nucleotides so far. If you think about high and low, there's going to be 16 total possibilities, right? This could be high or low, this could be high or low, this could be high or low, this could be high or low. So you could do the 16 possibilities one by one. But what I'm going to show you is a way to cut that down. Okay, so you'll see how I do much fewer computations than I would have done if I tried to find the probabilities for every possible sequence. Okay, so let's go on to the next one. All right, so here's the next stage. I know at this place I have 0.15. Now, what's the probability that it goes from G high to, and I know the next one is G also, right? So what's the probability it goes from G high to G low? Well, I know that if it's going from here to here, it's going from high to low, and that's the 0.5. And then I also know that the nucleotide here is G. That's the 0.2. Okay? This 0.5 comes from this transition probability. The probability of going from high to low is 0.5. Okay? The probability of going from high to high is also 0.5. So if you see this here, I also have a 0.5 here. But I multiply by 0.3 because the probability of G in the high state is 0.3. Okay? So I have to, for my total probability, I need to multiply this probability, which we would call prior probability, times this transition probability. And that's going to give me the total probability of high G, high G. Okay? So so that gives me 0.15 times 0.15, that gives me this number here. Okay? Now, that's not the only possibility for ending up in high G. It's possible I could go this way. Another possibility would be to go this way. I could go to low G and then high G and still be ending up in high G. Okay? But what's the probability of that eventuality? Well, that eventuality means in the first stage I'm in low. Now to go from low to high, it's 0.4. I'm not going to keep going back to my diagram, but the transition probability from low to high was 0.4. And the probability of being G high is 0.3. Okay? So I need to multiply this value times this 0.1, and that gives me the 0.012. All right, now, which of these is bigger? Well, the one that didn't cross out, right? So I can eliminate this possibility and say the best of those two possibilities is this one. I don't need to consider this one anymore. Okay. Now, the fact that I've eliminated this possibility also means that I've eliminated any other possibility that continues this possibility. So I've eliminated lots of possibilities simply by comparing these two. So you see, this is the whole idea of divide and conquer. Now I do the same thing down here. I could end up in G low. There are two ways for me to get to G low. I could go this way, or I could go this way. I compute the probabilities for both of those. I take the bigger one, and I retain that. Okay? All right, now you can see, I hope that you can see, that I can simply continue this process. I only have two possible best paths up to this point. Right? Now I can continue the process to the next stage, And it's exactly the same, whoops, sorry, skipped too much. Okay, so I continue the process to the next stage. I start with these probabilities. I don't even need to save these probabilities. The only thing I care about for the next stage is the result I have at this stage. Okay? So I save this stage, I save the history, and then I compute the next stage probabilities. I have two possibilities. I could go from here to here or here to here. I compute those two probabilities. I choose the best one, and I throw out the one that's worse. Same thing here. If I end up here, there are two ways. I know I've gone this, I could either go this way or this way. I compare the two possibilities. I save the one that is best. So what do I have stored here? All I need to store are the two values and the two paths that go to those two values. Okay, so I don't need to use a lot of storage. Okay, so now I just continue the process. Oops. Okay, so at this point, suppose I only have a sequence of 4 nucleotides. Then my best would be to choose the best of these two. But if I continue, I just need to keep going. So at the very end, I will choose which of the best of these two values. But as I'm going on, I need to save both, because I don't know which one I'm going to end up in. Okay? So like I said, if I only had 4 nucleotides, I would end up choosing this path. I would say high, 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 low, because that has the biggest probability. But I could also, if I was going to continue, just continue the process, and it works the same way. Now, Professor Foley told me that I shouldn't show you code. I'm going to show you code anyway, because I really think that you people, both faculty and students, really need to learn Python. So this is my advertisement for Python. And I have a tutorial for Python. It's not for sale, but I can share it with you. All right, so just to show you the structure. Now, I also want to show you really how simple it is. If you break this down, if you look at it, the code is really extremely simple. This is all initialization. I'm just setting up my variables, arrays, and so on. The entire computation is here. That's the whole code. This is the entire code that solves the problem. Okay. So I have to put in my initial sequence. I need to store my optimal sequences as I go, and then I need to put in the transition probabilities. I need to put in both transition between high and low and the nucleotide probabilities in high and low states. And then I need to store some things to perform the intermediate computations, and that's what I do. Then here I go take my sequence one by one, and then I compute my current probabilities, and then I do the comparison. And if the comparison gives one of the sequences, it stays the same. If it doesn't, if it gives the other sequence, I have to switch the sequence that I store. And you see really that the guts of the computation is right here. Okay? So if you organize your computation well, it's very simple. Another thing I want to point out is that this relies very heavily on matrix mathematics. There's a matrix multiplication here. Actually, the matrix multiplication is right here. Python can do matrix multiplication extremely easily. I was talking to Professor Gaunt about comparing Python to Fortran. For Fortran, you have to write 2 loops to do this. So I can do this in one statement. There's probably be 10 lines of code in Fortran. It's 1 line of code in Python. Okay. And actually, since I'm advertising Python, I might as well go the whole hog. I heard someone talking about Anaconda. So this is Spider, which is part of Anaconda. It's what you call an IDE, Integrated Development Environment for Python. And so if you get Anaconda, this comes with it. And this is the same code. Whoops. Sorry, that's something else I was going to show later. But let me just run the code. It just runs over here, and it gives and there's the sequence. There's the sequence that comes out. And I can easily modify my sequence up here, and I can change the sequence here. Here I have 0 equals A, 1 equals C, and so on. If I wanted to change these numbers here, right, I can easily, whoops, what's going on here? Right, I can just change that and run it, and it will give me the new answer. So Spider is very easy to use and very powerful. And if want to get introduced to Spider or Python, I would be happy to talk with you further. I can say I'm a Python evangelist. Okay, so, all right, so, all right, now, so let me go on to something a little more complicated. I mentioned Lucas Brent, my military student, and he was a controller, which means that he took care of the money for a brigade in the Army. This is the size of the budget that he managed. Now, if I had that much, I wouldn't be here. But anyway, he was my student, and one of the, and then this headline is very interesting. U.S. Army fudged its account by trillions of dollars. And he told me that, in fact, this is true. It doesn't mean the money is being misused. It means that it's not being accounted for properly. And that there are sometimes when they have items that are millions of dollars that they can't figure out where it came from or where it's going. And the problem is that the accounting system only records partial information. What they do is they record orders and they record pay. So let me see. I forget what they're called. We'll say in a minute. But they record the orders that they make, and then they record the money that goes out. But they don't match up the orders they make with the money that goes out. Okay. So there's money. They are asking for things, and they are getting materials. They're getting equipment, trucks, and planes, and so on. And they're paying the money, but they haven't matched the money they pay to the things that they're getting. Okay. And there's some delay. Of course, there's some delay between the order and the time that the thing comes. So sometimes you might make an order and it didn't come, and it's not tracked well in the system. Okay. So the idea that we were looking at was to look at the system, look at the orders, and then look at what is received and try to match these up. So it's a matching problem. So this is what you call them. You call orders and obligations. The order means I want a truck, I want an engine, I want a helicopter. Okay. Obligation means they take money out of your account. Okay. So of course, if you make an order, the obligation will come later. And there's a variable delay between the order and obligation, up to 8 days. So there's no record of which order produces which obligation. And besides this, there's an additional complication called credits. Because if you return something, if you return equipment, you return an engine or something like that, you will get credit from the manufacturer. And these aren't tracked either. Okay? So even the orders and obligations, they're not going to match exactly because you're also getting credits. So there are these three things being involved in the budget process. And credits also occur at random times. They're not recorded in the system. Okay? So what I want to do is make a simple representation of this system and try to analyze and try to do the best possible job I can to match the orders to the obligations. Okay? So as I said, there's some aspects of the system. You have a regular delay. You actually have two different types of orders. I don't want to get too much into the details because I want to present the method. Okay, so in this case, we had lots of actual data. So we used 4 months to test, 5 months to do prediction. And of course, you do have various complications because what do you do with weekends? So there are some things you have to deal with. All right, so here's a kind of a schematic way. So these are the two different kinds of orders. There's the regular and there's the exceptional. And here's the obligation. Obligation is when the money goes out. So if I order at this time, it will obligate some other time. It will obligate some time later. So the idea is for each order, you want to find out where it's going to be obligated. Okay, so that's kind of a simple idea. And what you want to do is get the very best matchup between orders and obligations. So I use this kind of technical term. I want to minimize the negative log likelihood. But this is not a probability class, so I'm not going to get into that. The idea is just that I want to make the best possible matchup between my orders and my obligations. Okay, so I only know that if I have an order, it's going to obligate sometime within 6 to 8 days, within 6 days or within 8 days. I don't know where, and I want to make the best possible matchup. Okay, so let me simplify the case here. Let's suppose there's only one source of commits, and the commits must obligate within 6 days. Okay, just to simplify. But the idea will be the same when we have a more complicated system. So we want to find the commits that are obligated each time. So at any time, if I have a commit, or if I have I should say commit is the same thing as order. I have an order, it either could have been paid for or not. right? It's possible that it was already paid for, or it's possible that it's not. So for each possible order, it's either in obligated state or not yet obligated. Okay, okay, so obligated means it's paid for. Non-obligated means that it's, I represent that as 1. Okay? All right, so at any time n, you're only interested in the orders or commits that occurred during the previous 6 days. Because if it was before 6 days previously, it couldn't possibly be obligated at that time. So that means that I can represent the current state of the system by 6 binary digits. I look at the previous 6 days, I look at whether it's committed or not, and I have 0 or 1 for each of the 6 previous days, and that will determine the current state of the system. All right, so here's a simplified example. These commits are data that I would receive from the Army, so this is actual data that I would receive. The obligations are also data that I would receive from the Army, and then here I have the day index, and on the first day, sorry, the first day, if I have obligation here, well, there's nothing that it could have committed, so there's really nothing that could happen here. Now on the second day, let's just slow down. All right, so on day 2, any commit on day 1 cannot obligate on the same day. If you make an order, it can't be paid for the same day. So if I'm looking at obligations on day 2, then I know that this commit here is a possibility. It has not yet been obligated. It's not yet been paid for. So it's possible that this commit will be paid for on this day. I don't know if it has been, but it's possible. So I need to evaluate that possibility. So that's, and in fact, that's the only possibility. So this one has a commit. So this commit either could have been obligated on this day or not. Those are the 2 options I need to evaluate for day 2. Either this commit has been obligated on this day or not. And then I continue. Now, on day 3, I have 2 prior commits. So it's possible. So as I said, this one can't possibly have committed on the same day. So this has not yet been committed. So that's why there's a 1 in both of these second places here. But it's possible that the first one was obligated on day 2. So it's possible that this one has already been obligated. So these are really the 2 possibilities for the states of the system at time 3. So I just keep on going like this. And you see it gets longer and longer. Right? And really the possible commits here, if you think about what they are, they're all possible binary strings of length 5, except the last one has to be a 1. Okay? So there's 16 of them, right? Because there are 2 here, 2 here, 2 here, 2 there. There's 16 possibilities. The last one has to be a 1 because by day 6, the commit 5 has not obligated yet. So I need to evaluate all of these possible states and all the possible transitions from these states and all the possibilities for these to commit on this day. And then I need to minimize, I showed that function that I'm trying to minimize, I need to minimize that function over all the possibilities. Okay. All right, so what happens is, as I said, on the 7th day, the state that describes my system are all possible binary strings of length 6 ending in 1. Okay. Right. And then as I move on from there, as I said, in this case, on day 9, I don't worry about the commits before day 3 because it's already too late. Either they were obligated or not. And so I don't have to worry about those. Okay. All right, so here I have my trellis. Now remember when I did the DNA, I had a very simple trellis with 2 states going to 2 states. But now we have a more complicated trellis. Now my states are described by a series of binary digits. Now I mentioned in the previous slide that I actually have 6 binary digits. I'm just doing a simple case where I only have 4 binary digits and the last one is 1, okay? Well, it's not possible to go from every state here to every state here. So you have to figure out the structure of this trellis. these states can only, this state, for instance, can only come from 4 possible states. So if you remember how I did in my DNA, on the right I had 2 states, on the left I had 2 states. Each one of these states could come from 2, and this state also could come from 2. And I needed to compare those 2 states and find the best one. In this case, I'll have more states to compare. But the idea is the same. I just need to compute these 4 transitions, find the best one, and I assign the best one to this possibility. Now you can either look from the destination point of view or from the source point of view. From this source, I could go to 4 possible states. Not all transitions are possible. So I can construct a trellis. Okay. So this is a more complicated trellis. In this case, the colors represent which state it's going to. Right? So you see all the red are the ones that go to this state, and so on. And once you construct this trellis, you'll have the same trellis from time to time. It works the same. So you can see that once you set up the basic structure, you just put this inside a time loop and you run it again and again. It becomes automatic. Okay, so this is the full trellis. Okay, and this is an outline of the code that you would write. You have to go through the times, then you look through the source states. For each source state, you look at each transition, then you evaluate the result for the transition, you compare it with the result you already have, you replace if necessary, and go on from there. Okay, so if you want more details, I can share this presentation with you. So I just talk about, we did verify this on data and found that this method gave 100% correct match when we had the data and we knew which source and obligations came from which. Okay? And we ran this on data, and what really validated this for me was we ran this on data, and we found a commit, an order that was not accounted for. And he went and Lucas went back into the record and found out it was an actual mistake. So we were able to locate mistakes in the budgeting using this method. Okay. And Lucas told me that, in fact, the year before he did this study, I think there was a disparity of something like $2 million in the budget at the end of the year. And after doing this study, I think the disparity was less than $100. So hopefully we save the taxpayers some money. Okay, so whoops, there's more. Where did it go? Oh no, I know, I put it somewhere else. Okay, so let me just, all right, yeah, good. We're at a good time. It's only 40 minutes. Let me give another application. This is a little bit more sketchy because I didn't put this into a PowerPoint. Another thing that I've been working on recently is optimal control, and the control in the spread of disease. Now, when you have a disease, you can, like for instance, some infectious disease. Actually, I started this with a plant disease called anthracnose, where the disease spreads from plant to plant. And you have various options for control. So in this example, I just say you have a case in a system with a finite number of control options at each time. So for example, in disease control. So the system has 3 functions of time. You have the state of the system, the cost rate, which would be the cost involved in the system functioning and also in control. And you also have the level of control. So you have the system state, cost rate, and the applied control. So in this practical example of disease, you could say that the state is the proportion of the population that's infected. Maybe 10% of the population is infected. And U would be how many people you're vaccinating over time during that time period. And then C would be the cost. Now you have a cost involved in vaccination because it costs money to vaccinate. You also have a cost involved when people are sick because they're not productive. So you have to come up with some kind of cost function that depends both on the state and on the control. Now, this system is what you call Markov system, which means that if I know the state, okay, very good. If you know the state at a certain time, and you know the control subsequent to that time, then you can tell what the state is at the subsequent time. So in other words, the future only depends on the present. So that's what you call Markov. And that simplifies the analysis quite a bit. And then the cost depends only on the state and on the control. And the total cost is the integral. So the integral is a sum. You can sum this. Now you can actually apply dynamic programming two different ways. So I have a very simple schematic here. So because if I want to compute this numerically, I will need to discretize time, and I'll also discretize my state space, which means I set certain levels. You know that the infected proportion could be 11%, 15%, 15.7%, but I'll discretize my level of infection maybe at levels of 2%, something like that. Now, if I'm at time zero, I have, let's say I have three different options for control. I can do an intensive vaccination, which would drive down the level a lot. I could do less intensive, or I could do no vaccination at all. Now, with those three options, then two things happen. You'll have three different resulting states, right? And you'll also have three different costs involved, right? There's a cost involved in people being sick. There's also a cost involved in the vaccination. So you'll have a cost involved with each of these three. Right? So that means that from here, depending on which control I use, I have three possibilities. At this point, I don't know which one I'm using, so I need to keep all three possibilities in my memory. So let's go to the next state. If I start from here, I'm going to keep accounting for these three possibilities. For the next state, depending on what I do, I have three possibilities from here. Now, you can see that I could go this way, I could do this option here, or I could do this option. I end up in the same place. So what do? The same thing I did before. I compare these two, I take the best one, I only save the best one. So as I'm going on, you could say I'm pruning this tree, and I only have one branch to each one of these ending states. So instead of keeping all this large thicket of branches, I only keep one branch to each of these. And then I continue on. And in the end, I'll have some branches here, and I'll choose the one with the lowest cost, and that will be my final answer. So that's one way to do it. Now, of course, one problem with this is that often your state space does not have a single dimension. Right? In this case, I just have people sick or not sick, but there might be multiple dimensions. There might be, you also have people vaccinated, unvaccinated, people, you might have some age structure, something like that. So if you have multiple dimensions, this becomes very difficult, because you would have to discretize each dimension, and that means you have to multiply. Like if I have three different aspects to my state space, and I discretize each one in 10 levels, that's 1,000 different levels. So the number of states becomes very large. But the nice thing about a computer is you can deal with states of 100,000. You can deal with 100,000 different states. So you can actually do quite a few dimensions using this method. Okay. Now there's another variation of dynamic programming called backwards programming. And the idea about backwards programming is that if you work from the end, then you're actually keeping account, because the present only depends on the future. So if you work your way backwards, you can find, you don't have to save many possibilities. You can know which is the best one. So you don't need to save all of these different possibilities. You can use the same methodology to work backwards. So you can identify a unique optimal control solution that ends in a particular state. But so that's the problem, is if you start with the end state, I can find